in the previous video, we ended by talking about the fact that the wave number or frequency of the peak, its intensity and shape are all important characteristics of a peak in an IR spectrum. And we're going to look at these in a little bit more detail. So one of the things that makes IR spectroscopy so useful is that specific bonded atoms or functional groups will have very similar signals even when they're in different molecules. And so, as an example, this is an IR spectrum of an alcohol, 2-butanol. This is an IR spectrum of another alcohol, 2-propanol. And this peak in particular is characteristic of the OH stretch of an alcohol. And you can see in both of these alcohols, we have a very similar looking peak in both of those spectra. And it's similar in terms of its frequency or its wave numbers. It has the same broad shape, and it has similar intensities. And so anytime we have an alcohol in a molecule, we would expect to see a peak that looks very similar to these peaks. And that's not just true for alcohols, but many bonds in molecules will have these similar reproducible peaks. And so what determines the frequency or the wave numbers where a peak is going to appear in the IR spectrum? Well, it depends on two things. It depends on the strength of the bond and the mass of the atoms that are connected by that bond. So if we take a look at the first one, so the strength of a bond. And so we know that when we go from a single bond to a double bond to a triple bond, they get stronger. So of these three carbon-nitrogen bonds, the single bond is the weakest and the triple bond is the strongest. And you can see how that impacts the frequencies of electromagnetic radiation that those bonds will cause the molecule to absorb. So the weaker bond has the lower frequency, the stronger triple bond has the higher frequency. The other thing that determines the frequency of the electromagnetic radiation will be absorbed is the masses of the atoms that are connected by that bond. So as an example, we have a carbon connected to a hydrogen, an oxygen, and a chlorine. And so the carbons are all the same, but hydrogen is the lightest of those second atoms, oxygen is heavier, and chlorine is heavier still. As you can see, the lighter the atoms involved, in this case the hydrogen, has the highest frequency. As the mass of that partnered atom becomes heavier, the frequency gets lower. So stronger bonds and lighter atoms give rise to higher frequencies. Now, we know that carbon-hydrogen bonds are some of the most common bonds that we find in organic molecules. And so they're particularly important in IR spectroscopy. And so whether that carbon atom is sp3 hybridized, sp2 hybridized with a double bond, or sp hybridized with a triple bond, all of these CH stretches absorb similar frequencies of electromagnetic radiation. And while the differences are small, they're important. So an sp3 hybridized carbon CH stretch is just below 3000 wave numbers. If the carbon is sp2 hybridized, the CH stretch is a little bit higher frequency at about 3100 wave numbers. And for an sp hybridized carbon that's part of a triple bond, the frequency of that CH stretch is even higher at about 3300 wave numbers. And so when we get to analyzing specific spectra, I'll come back to this point again, about the difference between the hybridization of the carbon in these CH stretches. This isn't something I'm going to ask you a lot about, but it comes up a fair bit in the textbook, and so I wanted to at least mention it. And that's how resonance influences the frequency at which a carbon-oxygen double bond absorbs. And so a typical ketone will absorb at a frequency of about 1720 wave numbers. If the pi bond of our carbonyl group can participate in resonance, as it can in this case, it lowers the frequency somewhat. And the reason for that is when we consider the resonance of this conjugated ketone, there is one additional resonance structure that doesn't appear in this ketone. And so now we have two prominent resonance structures that feature a single bond between the carbon and oxygen. And so the double bond in this ketone is a little bit weaker than the double bond in this ketone because it has more single bond character. And that's why the frequency of the absorption for this conjugated ketone is a little bit lower than a standard non-conjugated ketone. Okay, so shifting gears, we talked about what influences the frequency at which a molecule will absorb radiation. It depends on the bonds, it depends on the strength of those bonds, and the mass of the atoms. So what determines the intensity of a signal, right? How strong or deep that signal is. Why would a molecule have a strong signal versus a weak signal? So in order for a molecule to absorb infrared radiation, the dipole of the molecule must change as a result of that particular vibration. And so if I have two carbons connected by a double bond, the electronegativity of those two carbons is obviously the same. And so when this carbon-carbon double bond stretches or contracts when it vibrates, the dipole moment of the molecule doesn't change all that much. But when I have two atoms with very different electronegativities, like carbon and oxygen connected, in this case, the dipole moment of the molecule changes quite a bit as this bond stretches or contracts. And so a carbon-oxygen double bond typically gives a more intense signal than a carbon-carbon double bond. And so not all bonds or vibrations in a molecule will cause that molecule to absorb infrared radiation. And if a bond is completely or highly symmetrical, then we may not observe that stretching frequency in the IR spectrum. And so this molecule is an example of that. So typically we would expect to see a carbon-carbon double bond around 1600 or 1700 wave numbers, and we don't see that in this molecule. That's because this molecule is perfectly symmetric, and so essentially the dipole moment doesn't change at all when this molecule vibrates, and so we don't see this stretch in the IR spectrum like we might expect. Alright, so the intensity of a signal in an IR spectrum is partially determined by the differences in electronegativities of the atoms connected by that bond and how symmetric the molecule is around that bond. But another thing that influences the intensity is how many of those bonds there are in the molecule. And so even though CH bonds are not considered polar, we often see strong signals or intense signals due to CH stretches just because there are so many of them in the organic compound. Alright, our final characteristic of an IR signal that we're interested in is the shape of that signal. So some peaks we see in the IR spectrum are relatively broad and some are narrow. And I think in the very first example on this video, we talked about the fact that OH stretches often give broad signals. And so the shape of the signal can help us to identify what types of bonds those are coming from when combined with the intensity and the frequency of that signal. And so we're just going to look at a couple examples of some common shapes of different signals. And so the first one I want to look at is carboxylic acids. And so if you see this really broad peak in the IR spectrum, it goes from roughly 3,400 wave numbers down to 2,400 wave numbers. We don't often see peaks this broad unless we have a carboxylic acid. And sometimes these are described as a hairy beard, so sort of think Gandalf or Dumbledore, I guess. Right, so we have these sort of the overlap of the CH stretches with the OH stretch in the carboxylic acid gives this characteristic hairy beard signal. And then carbon oxygen double bonds that appear around 1700 wave numbers. Since a carboxylic acid, let's draw carboxylic acid so we're all clear what I'm talking about. Right, carboxylic acid has both the OH and the C double bond O. And so if you have a carboxylic acid, you'll see both of these signals. But the hairy beard, that's a dead giveaway. We have a carboxylic acid, and that's specifically the OH from the carboxylic acid giving that hairy beard. All right, so the two spectra that we're seeing on this slide are coming from amines, right, where we have nitrogens in our organic molecule. And if I have just a single hydrogen attached to that nitrogen, then we typically see just one peak in the amine signal. And this is what we call a secondary amine. Secondary, put the R in there. Or sometimes you'll see people use the abbreviation a 2 with a degree sign. That's telling you that it's secondary. When I have two hydrogens connected to the nitrogen, this is called a primary amine, or we might use a 1 with a degree. And where this secondary and primary comes from is how many carbons that nitrogen is attached to. So if the nitrogen only has one hydrogen, then it's attached to 2 carbons, hence secondary amine. Or if that nitrogen has 2 hydrogens, then it must be connected to 1 carbon, and so it's a primary amine. But the secondary amine has a single peak. A primary amine has 2 peaks. And this is because the hydrogens can either undergo a symmetric stretch, where the 2 hydrogens are moving away from and then back towards the carbon at the same time, or the primary amine can have an asymmetric stretch, where as one hydrogen goes towards the nitrogen, the other one's going away, and vice versa. In a secondary amine, we can't have symmetric and asymmetric stretches. It's just the NH stretch, and so we only see the one peak. Alright, before we go on to the next video, I just wanted to finish by talking about what we call the fingerprint and the diagnostic regions of the IR spectrum. And so, oftentimes we're going to divide our IR spectrum into 2 pieces. We're going to put a line at 1500 wave numbers. Everything below 1500 wave numbers is what we call the fingerprint region. And this is where mostly our single bonds show up. And this part of the spectrum can be really complicated and difficult to analyze. And so typically, we're just going to ignore the fingerprint region. And we're going to focus on the diagnostic region. And so there we're going to find our double bonds, our triple bonds, and then bonds of hydrogens to things. And so in the next video, we're going to get very specific about how we want to go through and analyze these IR spectrum.